I'd like to say thank you very much for having me here. This is my first real trip to London. I've been in the airport a number of times, but I never actually got into the city, and it is a wonderful place. I understand why everybody loves it as much as they do. Thank you for the introduction. I am indeed a statistician at the Jet Propulsion Laboratory. JPL is effectively a US national lab. We are operated for NASA by the California Institute of Technology, the same way that, for example, Los Alamos National Lab is operated for the Department of Energy, used to be by the University of California, and I don't know who runs them now. But and we are NASA's lead center for the robotic exploration of space. Every NASA center has started out having a specialty, and Johnson Space Center is for human flight. Kennedy is the big launch place. The big center for Earth science is Goddard Space Flight Center in Maryland, and the big center for anything that's not Earth, that's out in the universe somewhere, is JPL. We did the Mars rovers, you may be aware of that. That said, we still do quite a lot of Earth science work. The business line, if you like to use that kind of an expression, for JPL is to build and fly remote sensing instruments and study the data that come back. Now, all NASA data are free and publicly available to anyone that wants them, if you can figure out how to get it and if you can figure out how to use it. That's the catch. My talk today is about, I'll tell you straight up, this is the first time I've given this talk, so please forgive me if it's a little rocky. This is something I've been thinking about for a long time, which involves the problems in obtaining and working with and analyzing remote sensing data. But I do know that this problem infects a lot of areas, not just Earth and space science, but it's a problem in medicine, where you have different hospitals that all are trying to feed their data to some network of repositories. They're part of a network of repositories, and researchers want to access data from different hospitals and use them simultaneously. And we have the same sort of issue with our remote sensing data, because our data are stored in distributed places. And since the world is getting to be one big community anyway now, there's the European Space Agency, there's the Japan Space Agency, there's the Indian Space Agency. All of these places have their own way of storing and delivering data to scientists. Let me credit the co-authors here. This is a topic that we're focusing on. I've called it the theory of data systems because that attracts positive attention from JPL and NASA managers. And this is the subject of one of the sub-working groups of the remote sensing working group that is part of this year's SAMSI program on mathematical and statistical methods for climate in the Earth system. The two primary co-authors are Maggie Johnson, who's a postdoc at SAMSI now and will be, I'm proud to say, doing her second year at JPL. We finally made that happen. It wasn't easy. Brian Rich, who's faculty at North Carolina State and who's supervising Maggie right now. And too many people to list on the slide who belong to the working group that's thinking about this. So there's a quick outline. I'll just go for it. I won't try to editorialize. Okay, so when I first got to JPL, which was in the year 1999, which was the year I got my PhD, I learned about, I've been working on the science side of the operation with, I started on the MISR team, and I learned that NASA flies all these instruments and collects all this remote sensing data, and they ship it to the ground. The instruments that fly in space, I don't know if everybody knows this, maybe you do, maybe you don't. Nobody carries a thermometer into space. That's not how it's done. Remote sensing satellites count photons hitting detectors, and that's all they do. And those data are dumped down to Earth, and they go through an enormous amount of data processing to essentially infer the state of the atmosphere or the state of the land surface from those radiant spectra, we call them. And that process is fundamentally an inference. although my physics friends at JPL didn't seem to realize that. So there is a whole great deal of interesting work to be done there in looking at the way these algorithms are, the way these algorithms do the inference, and thinking about how to put uncertainties on that inference. Because, in fact, many of these teams use a version of Bayes' theorem. They call it optimal estimation over there. But they don't pay very much attention to uncertainty. That's something that we're highly involved with at JPL right now. When Doug mentioned observations in his talk, he talked about using statistical methods to help track the uncertainty, but you can't do that unless the incoming data have reliable uncertainties on them in the first place. And at present, that's not really true. So we think there's something big to be done there, and we're working on that. Anyhow, once you have these, what we call geophysical or level 2 data products, level 1 data products are these raw radiances that come down from the satellite. Level 2 data products are things like data sets that have atmospheric temperature, land surface type, the amount of water in the atmosphere, the amount of CO2 in the atmosphere. These things are shipped off to what are called distributed active archive centers, and where they're stored and served to the public. And they're done, the DACs, as they're called for short, are discipline specific. So you have, I won't use that, you have, you can see in green on the slide here what the sort of the themes are for the different data centers. The Goddard Space Flight Center, that's GSFC. Earth Science Data and Information Center has mostly the atmospheric data and ocean data. JPL has something called the Physical Oceanography Data Center, where we have more data on ocean things like sea surface temperature, ocean wave height, things like that. There's even a, I'm looking for it here, there's a land processing center, well, you can see for yourself, I won't belabor it. You get the idea, right? So data on different kinds of processes are stored physically in different locations. And the bedeviling part of this is that these DACs were really intended to serve data, right? To throw data over the transom at the user community and say, here you go do great things with it. But because of the volume of data that we're collecting now, this doesn't make a whole lot of sense anymore, I think. It doesn't make sense anymore to separate data distribution from data analysis, because the old-fashioned paradigm of you're a scientist, you sit there, you download all the data that you can get your hands on to your own computer. While it is really good for employing graduate students who can sit and spend months just waiting for data to FTP, it's just not an efficient way to do science anymore. So it was that problem that sort of drove us to thinking about the things that I'm talking about here, that I'm going to talk about. The other thing to remember is that I think maybe I'm already into my talk. These data types are new types of data. They're not suitable for whatever Mathematica already has as its canned way of doing cluster analysis or something like that. They're new types of data intended to answer new types of questions, and there is a need for new research to develop methods that are specifically aimed at that kind of data and those kinds of questions. Often, one wants to do an analysis that involves getting data from more than one data center. There's no monolithic data set out there anymore that says, this is the data set you want to do your analysis. You might want one variable from one data set that's housed in Pasadena, and you might want to correlate that with data from another variable from another data center or from an ESA data repository somewhere on the other side of the world. And simply, like I said, bringing these data sets together is just too hard. So you can imagine a day when you assemble the data set you actually want in a streaming fashion on the fly as you carry out your analysis. So maybe I can't bring over all the data for the last 20 years from MISR on cloud top height and all the data from the last 20 years on cloud fraction from some other instrument somewhere else, but maybe I can bring it over in chunks and process it as I need it to go through my analysis. And if you start thinking that way about the problem, I call that data analysis choreography. How big should the chunks be? You know, do I get a chunk from this place and a chunk from that place and do something to it and then bring in a third thing? Or do I get these two first and then do that? There's all kinds of questions there about how you might want to organize an analysis when you're working in an environment where the data are all over the place. So I'm not really talking about distributed computing here, although I could. It could be a case. You could also imagine that it would be very handy to be able to do at least some computation on the servers where the data reside. It's a very natural thing to do, and I know our little working group wants to look into that, but I have restrained them to thinking first about the problem of just the problem of how you get the data and how you bring it together, and what makes for an efficient way of doing a particular calculation. And you'll see what I mean in a minute. The other problem with just copying data down is then any time data change, and it does change because people are constantly reprocessing their data, if you bring the data over and you don't know that somebody has reprocessed because they found a mistake, then you're going to go and try and publish your scientific result or tell your applications manager to go ahead and evacuate Miami, Florida, and you're not going to realize that that's not really right anymore. So in particular, one of the things we've been interested in is how one might use spatial statistical algorithms in an environment like this. It's hard enough if all you're going to do is you want like a global average temperature. But you can imagine what you would do. If you had computing resources on each of the machines, you would compute a sufficient statistic on each of the machines and then only move this reduced piece of data to your machine to finish the calculation. But in spatial statistics, typically you've got a bigger problem because you often need regions together so that you can estimate spatial structure, spatial dependence, for instance. Supposing you don't know how long the correlation length is for a particular process you're interested in, what are you going to do? You're going to have to do some kind of a pilot study to try to figure that out, and then you're going to think to yourself, well, okay, I found that I only really need data within 45 kilometers of the site I'm interested in, but then I move to the next site and it's a different 45 kilometers and so forth. Okay, so I have just a couple of examples of the kind of places where this might be an issue that even aren't spatial statistics. One is something Doug mentioned, the comparison of observational time series to climate model generated time series to try to say, hey, these climate models are supposed to be predicting what the, how much CO2, how much warming there's going to be in 20 years or 30 years, well, it sort of seems reasonable that if the physics of the climate model are correct, then it ought to be reproducing what we have observed in the past and present. And so there's some value in wanting to make that comparison. This is something, I made this, but it is actually something you may have seen before. It's a time series plot of the monthly global average surface temperatures from 44 different CMIP5, that's the Coupled Model Intercomparison Project, 5 climate models, estimates or predictions of atmospheric global surface temperature from 1918 to about 2003. And then the red line is the go-to observational data set that's most often used for this comparison, called the Hadkrut-4 observational data set. And the black line is a smoothing, a moving average smooth, so you can see it a little bit better. And it's really hard to look at that and make a lot of sense out of it just by looking at it. So if you wanted to do anything more, more nuanced, let's say, what you would have to do is you would have to download the data from these 44 different models, and you actually need to get them from 44 different modeling centers. Now, there are tools out there. There's a very nice set of tools out there that something called the Earth System Grid that make it look like you're only going to one place to get these things. But in fact, the data do belong on many different computers. What the Earth System Grid does is it has a metadata catalog that automatically redirects your query to the appropriate data center to get the data. But you still have to download it. You still have to bring it all to you. Here's something that I just stumbled on by complete chance that I really like, called the KMI Data Explorer, which is another web-based interface for getting climate model output and observations that can be used to compare to. And this is really nice. It lets you, shows all the models, shows all the variables, shows all the different ensemble members of different models, lets you, with radio buttons, click on what you want. It does some remote, I'll call it computing, in that it will let you select out space-time subsets, and it will even let you create some averages. And it will display plots for you, which is really nice. But you can only do what they let you do, right? And scientists tend not to like that. I know I don't, and I'm not even a physical scientist. What we really want to try to do is to come up with a way to let people do their own analysis, short of letting everybody do anything they want on the server, which would be great for the users, but not so great for the people who own the servers. And at the other end, short of having to just haul all the data over to your machine to do it. So the question is there something in between those two that we could reasonably hope to someday have in place? And thank you, Richard, who pointed out to me that free reign is R-E-I-N, not R-E-I-G-N, which is what I had thought it was. And it's even worse than that. I thought actually free reign meant the king can do anything they want. So it's not practical to let everybody do everything they want on a server, and it's also not practical to keep up with moving all the data to your server, so what can we do? And what are the implications for doing statistical analysis in an environment like that, particularly spatial statistical analysis? Since this workshop is about data science, I thought I would stand on the soapbox for a few minutes and say, I hate the word data science. I hate that term. It doesn't really mean anything. Everybody calls themselves a data scientist. So I wanted, the best definition of data science I could find came straight off Wikipedia as short for data-driven science, which I rather like. I think that's nice. There are other definitions out there. I also got these from Wikipedia, except for the last one, which came from David Donahoe's 2015 talk in honor of John Tukey. Jeff Wu's position was closest to mine. I thought it was just another name for statistics, but apparently not. And I like Nate Silver's definition, a sexed-up term for a statistician. But I am willing to admit now, that it's more than just statistics, certainly. It's something at the interface of numerous disciplines that have to come together to solve problems like the one we're discussing. So here's my definition of data analysis. I'll be a little more I'll narrow things down a little bit. It's finding structure in data either in a descriptive or explanatory context and potentially attaching quantitative measures of uncertainty relative to the population from which the data were taken to those conclusions. And I say potentially, not because we shouldn't, but because a lot of people don't. I think people would still say they're doing data analysis if they don't try to make an inference. At NASA, okay, so what's a data system then? At NASA, a data system refers to this giant processing infrastructure that downloads radiance data from the satellite, puts it through these very complex science algorithms to obtain an estimate of the true atmospheric state or the state of the land surface or whatever it is that's being estimated, and delivers data to the user community. So that's my definition. At NASA, we have something called the Earth Science Data and Information System, which includes the DACs, but also all the operational infrastructure that gets the data to the DACs. And on the planetary side, there's something called the Planetary Data System, from which you can download any image or any data set that was ever collected by any NASA planetary mission, which is kind of cool. The hitch is it's imagery. Right? It's not, you're not getting the data unless you know how to convert a TIFF file to numbers. But there are other places to get some of that. So we have a lot of experience with data systems.
Amy,
yeah.
How many people work on the EOS DIS?
Oh gosh.
Is it like hundreds or?
Yeah, thousands probably. Yeah, lots of them. Yeah. Okay, so what I wanted to do in this talk was to talk about about how to think about data analysis and the data system together. because I think that we are going to have to come to grips with the fact that we can't do everything we would like to do to absolute accuracy. So in exchange for getting better accuracy, we're going to have to pay more in some sense in terms of the time it will take us to get the data and the time it will take us to do computation. And it's important to know what the trade-offs are when you're obtaining data for something like that, because if you're a science person and you have a particular science goal inferentially, you may need, people often talk about needing accuracy to within plus or minus such and such in order to draw a conclusion that would be meaningful for an application or for a particular scientific conclusion. So for some of those efforts, that accuracy has to be really high. And it's going to cost a lot to get that if you want that. And you may have to make compromises elsewhere. But for other kinds of applications, you might not need that accuracy to be so high. So maybe you can get away with using less data or different data, or you can compromise. And I think it should be really important to the people who serve these data to users to know what that trade-off is and to allow users to choose how much they want to spend in order to get what they want. So when I talk about data analysis, I mean make an inference from the data in this talk. And I think we have to think about data analysis systems and rather than data processing systems separate from data distribution systems. We think here, and my colleagues and I, took us a long time to actually figure this out, that we tend to think of the data system as being fixed. In our statistical discussions, we never really contemplated the idea of being able to change the data system. And it took us a long time to convince ourselves that we could and should talk about that. We had to go out and learn a bunch of things about system architecture and software architecture in order to get a grip on this. So you could ask yourself, for a fixed data system, where a data system, I'll show you an example of a data system here. There's a data system, a really super simple data system that has one user on it, and it has capital J different servers that have data on them. And capital NJ is the size of the data that lives on each of those servers. The servers and the user have two-way communication. Note here that I've not said anything about communication between servers. That will come later. Not in this talk, but someday that will come in terms of our analysis here. So the only computation is going to take place at the user's system. So there's an immediate question that if you knew the kind of data analysis that somebody wanted to do, would you design the data system in a particular way to facilitate that, to make that calculation easier? Conversely, if you did have a data system that was already given to you, like the situation we're in today, are there ways to develop new statistical algorithms that might be able to more efficiently operate within that data system? And then there's the grand philosophical question, supposing you had neither and you were setting out from scratch, what would you do? So the example I'm gonna talk about with you guys today is a ridiculously simple example, but we felt that it was necessary to start at the most ridiculously simple situation that we could think of. And that situation is, supposing I want to estimate the mean from some data. So nobody's ever going to really want to do that here, but think kriging instead. So here's our data system with the capital J servers, and the cost to move data from server J to the user is going to be a function of two things. It's going to have something called an activation cost, which might be the cost of opening a connection to each of the servers. That'll be A sub J. And then there's going to be a cost to actually move data called B sub J, which is the cost per datum, let's say. So it's proportional to the amount of data you're going to move. And the little n's are going to be actually the amount of data you decide to move from server J. So those are the BJs. The user's computer has some kind of computational budget on it, which I decided to call kappa naught for no good reason. And as this little example proceeds, you'll see that doesn't really play a huge role at this point, but certainly whatever you decide to do has to require no more computation by the user than what the user has a budget for. That's the point of putting it there. NJ is the size of the data to download from server J. And now the problem. Let's say the statistical problem we want to solve is to perform inference on the population mean using data that is distributed across these J servers, and let's say the data have the following statistical properties. It's pretty simple. You've got yji is the ith observation on the J server. They all have the same mean. They all have the same variance. There is a correlation structure. So even though we're talking about the mean, there is a correlation among the data within servers and between servers, and that's what's going to makes this just a little bit harder than the super duper easiest bottom level problem, which would be IID data, independent and identically distributed data on all the servers. Let's see. Okay, so, and we're going to assume the correlation structure that's written here, and we're going to assume that these parameters that describe the both within server correlation and the between server correlation are known. So we're still trying to make things as easy as possible. Now we want to estimate the sample mean, and we all know how to do that. It's 1 over the total number of observations times the sum of the observations. That's the mean. And what's the uncertainty or the variance of that mean? Well, we can work that out. Because of the correlation, it's not quite as simple as it would be otherwise. It does involve those parameters, rho and phi. But you can see, I'm certainly not going to go through the derivation of that thing. Well, okay, never mind. You can see how it works out. It's a function of the parameters that describe the correlation structure and of the amount of data downloaded from each server. Make sense? Pretty simple so far. Okay, so our problem now, let's say what we want to do is we want to minimize that uncertainty. We want to minimize this uncertainty here, subject to a constraint on cost. So what are the costs? So total costs, let's say it's computational cost plus data movement cost, which is transmission cost, plus implementation cost. That's another thing that took us several months to realize we had to incorporate in all of this, that you have to put this in a setting where you don't have an infinite budget for building the data system. Otherwise, you would build an infinitely fast data system where there would be, you'd be completely unconstrained and you would do the full problem. So that's not really realistic for the real world, so we decided to stick implementation cost. So the computational cost we decided to make proportional to the amount of data that we're going to process. The transmission cost is going to be the sum of the activation cost times each of the BJs times the NJs. That seems pretty reasonable. And the implementation cost, I said, okay, you've got to pay those kappa naught dollars up front in order to buy your computer, in order to have a computational capacity at the user to start with. Then Maggie, the postdoc, made up this cost function for the data movement cost, and we don't believe it's realistic, but it will work. It's simply inversely proportional to how fast you want those A's and B's to work, right? If you want fast data movement, then you're going to have to pay a lot to have your A and your B be low. So it's just supposed to be inverse there. And the third piece there is what I would call storage cost. I have to be able to put the capital NJ data on each of the J servers. So there's my implementation cost. And let's just pretend for the time being that there are 5 servers and there's 100 data values on each server. And that kappa naught is fixed. My computational budget is fixed. So the data analysis problem here is to minimize by choice of how much data I download from each server. This formula here for the variance of the estimate, subject to a constraint on the cost, which let's call it Cmax. And I shuffled the numbers around a little in the cost function there, but I think I did it right. It was done late at night, but let's hope. You get the idea. So Cmax is some kind of overall cost constraint that I have to live within. And for the sake of being a simple problem, we are thinking of everything else here as being fixed from the data analysis point of view. Now, from the data system point of view, the problem is to choose the data system is characterized by the A's, the B's, the capital N's, where I choose to put data, and I think that's it. But in this really super simple problem, I'm going to say the capital N's and the kappa, they're all fixed. My data system design problem is to choose the A's and the B's that will minimize this cost expression here subject to a constraint on the uncertainty calculation. So I recall back to my days as an economics major, which I was an economics undergraduate way back when. And this is the one useful thing I learned as an economic undergrad, which is this idea that of analyzing things that trade off against each other. Another place where this shows up is in rate distortion theory, if you're familiar with some signal processing or quantization literature, where they talk exactly about this idea where you have the uncertainty is the suffering to the accuracy of your estimate at the back end or at the receiver end of a channel. When you take a random draw from some distribution and code it to be sent across a channel, then that channel has finite capacity. And the cost to you in that case is the number of bits you're going to need to use to encode that thing for transmission across the channel. So if you use lots of bits, that's expensive. I'm not sure why, but maybe the channel only has a certain capacity. You use a number of bits as cost, and this trades off in a way against the uncertainty, or what's called distortion in that world, of the answer. So I simply kind of stole that idea and put it down here, where now I've replaced cost with the cost functions that I showed on the previous slides. So here, there's a number of ways to think of this. It's convenient to think of it as a Lagrange multiplier problem. It's a constrained optimization where the Lagrange multiplier lambda is essentially a unit conversion that also tells you something about how much you value a reduction in cost versus a reduction in uncertainty. If you're a NASA person, in my shoes, for example, or in a friend of mine's shoes who works with these data systems, it's more likely that this is sort of what you have to deal with, which is that you have a maximum cost that you can tolerate, which is the C max. And if that's all you had, then you would say, wow, I guess what I want to do is I have to be under the red line, but I'd like to be in the place that has the lowest uncertainty possible, right there. If you're thinking about science problems, you might look at it the other way. You might say, hey, this data is only going to be useful to me if the uncertainty is at or below 0.4. So in that case, I want to be as low on the cost scale as I can possibly get, while in a way that the uncertainty never goes above that value. So there's lots of things you can do here. Going back to the Lagrange multiplier world, you can say that the slope of the tangent line to this curve at any point is a reflection of the relative value of cost versus uncertainty at that point. So you, as a particular user, might have a position on that curve that conforms to your relative evaluation of the importance of cost versus uncertainty, where now cost could be the time it takes to do the analysis, for example. Here's a different point on the curve where a small decrease in uncertainty is going to cost you a lot. So you might say, well, where would you really like to be if you didn't know anything else? You might like to be at the place where that, right here, close to the origin here. You might want to be there. All right, so here's a couple of examples that Maggie ran. Suppose we chose we wanted to be at that red dot. That's the position we want to be on the curve. If we go through and solve the optimization, which we can do because this is a stupid toy problem, it's very simple, we can do it in R. The answer for how much data should we download from each of the servers looks like that. We've allocated the size, those are the NJs over there, and the question of how fast should the A's and the B's be are over here. And there was nothing asymmetric about this. I think the answer could have come out with, here, any three of them. If you had a cheap AJ, something that worked quickly, the other two. I don't think there's anything special about which two came around. So now if I wanted to be at that other spot, I would get kind of a different answer. Okay, so in the same way that the rate distortion curve is kind of characteristic of a particular data set in terms of how it would collapse as you started to if you, for example, ran a hierarchical clustering algorithm on it that was based on a certain metric, this curve, this Pareto front, is a characteristic of the combination of the data analysis that you're doing and the data system that you're operating in. And it's this curve, I think, that we essentially want to try to be able to estimate. There are a number of component and relevant research areas here that I would call attention to. There's a lot of work on the so-called statistical computational trade-off. This was done in the theoretical computer science literature by Michael Jordan and somebody who's at Cambridge, I think, Quentin Berthet, and Venkat C, I call him because I can't pronounce his last name. Richard and a former student of his did some work on approximate sufficiency or approximate likelihoods. That's something we've been looking at. Matthias Katzfuss and Dorit Hammerling did some work on distributed data fusion, as odd as that sounds, that touched on this, and others. You can see them there. On the other side, this was probably the hardest part of this project, was getting our minds around the software architecture and the system architecture aspect of this. Because if you pick up a software book or system engineering book, which is the material that the people who build these data systems look at, it seems to be out of nowhere. It's just a set of principles. We've got pipelines and connectors. Okay, where does that come from? And it took quite some time to digging through it to realize, and some luck, having stumbled on a paper, this Baldwin, McCormick, and Rusnak paper, having stumbled on that where they tied principles of good system and software architecture to complexity theory, and to a paper by Herbert Simon from 1962 called The Architecture of Complexity. And it explains why in nature you find a lot of hierarchical systems. In economics you find specialization. And it's because it's more efficient, right? It's more efficient for me to learn how to build, build houses, and for Doug to learn how to build furniture than for each of us to do both. And I think this is where these principles of system and software design come from. So that's pretty interesting, actually, because we had one speaker we had a workshop about this in February, and we had one speaker there who talked about, he's a complexity theory fellow, and he does something called multi-layer networks, which I'm going to put that down there because A, it's fascinating. They've got beautiful visualization software. Multi-layer network is a network. It's like a network, but it's not just a single network. It's a bunch of networks where you can have connections not only within the given network, but between these networks. It's quite cool, actually. And there's a lot of mathematics behind having to deal with sort of a super network like that that's very interesting. And they've developed that already, so we're trying to work with them to start to think about how to do this. Each layer in this network might, for example, be a different part of the problem. One might be hardware, one might be software, one might be a data analysis, and you can imagine, in fact, I have a little thing, I'll put that there. There's my simple picture of a really simple multi-layer network. It's not even finished. It's got a hardware layer, it's got a random variable layer, and it's got a data layer. And we're sort of wondering what other layers should be in there. There's probably an algorithm layer, and these things are connected in such a way. So I'm just going to put that, just going to leave you with that thought. And I don't really have much of a discussion except a lot of questions, right? Like, if you're somebody coming in to try to use something like this, do you know what your lambda is? Do you know what your trade-off is? Is there a best one overall? Maybe. What if you can't calculate that variance in closed form, which is going to be a problem? I'm sure that's true. There will need to be some kind of resampling or bootstrapping methodology involved here, and that's going to require a bunch of thought because we don't want to have to bring things to the user for every iteration, right? So that's an obvious place where you'd want to have some kind of remote computational capability to do some bootstrapping remotely. How do you measure costs? I keep getting pecked about that by my JPL friends, and I don't know. That's coming. Everybody's so impatient, especially at JPL. They have attention deficit disorder. They don't want to wait. And lastly, the answers to these things, we said, in the simple example that I showed, we said, let's pretend we know what this phi and this rho are. We don't know that. We're going to have to figure out a way that we can do some kind of pilot study or or something to try to learn those things if we're going to go that way. So, and I close by saying, is this the quintessential data science problem? I started by saying I hate the word data science because I don't know what it means. But it seems to me if there ever was a data science problem, this is it, because it crosses the disciplinary boundaries between sort of data analysis and statistics and computer science and software and engineering and system architecture. And all those people who do that at JPL are called data scientists. And so if that's true, then this should be the kind of thing people are looking at. And I'm going to stop there because I see that we're almost done. I put references on here in case you're interested in reading about any of those things. That's it. Okay. Thank you.